This is the Amp Hour Podcast, released March 22nd, 2020. Episode 485. An interview with John Day. Welcome to the Amp Hour. I'm Chris Gamble of Contextual Electronics.
Hi, I'm John Day from Microchip Technology, and I'm a technical fellow and field applications engineer.
Hi, John. It's good to talk to you. How you doing?
I'm doing great, Chris. How are you?
I'm great. So we're going to talk to you about Microchip parts and how you've interacted with them. You've been there, if I'm looking at LinkedIn properly, 27 years. So no small feat in the world of modern electronics and stuff. That's a long time to be there.
Yeah, no kidding, Chris. It seems like it really flew by. It seems like it was yesterday that I joined Microchip. So, at the time, it was a very small, privately held, actually. It wasn't even public, near almost startup at the time. And it's been just a fantastic ride to see the company grow to where it is today, being, seeing customers really embrace the Microchip picks and some recent acquisition, Atmel and so forth. So.
Yeah. And tell me more. I mean, like, what was it like when you joined? I mean, I don't have a great timeline and I'm sure our audience doesn't either, of like when, Microchip's history and stuff like that, how you, what it was like when you got there.
Yeah, it's actually a pretty interesting story. So previous to Microchip, I worked at Digital Equipment Corporation, DEC, who's a now defunct computer company. And I was a senior hardware engineer, designing like I/O subsystem modules and, equivalents of FPGAs in today's technology. And then one of the fellows I had worked with at the time left Digital and became a regional manager at Microchip. And working at DEC, I had been, interacted with field applications engineers at companies like Philips and, Motorola and, other semiconductor companies. And I always thought that would be a really fun job, to transition into someday. And my previous manager called me up and said, hey, we've got an apps engineering job at Microchip. And I'd actually never heard of the company. And this is before the internet happened, before we actually had, you could just Google somebody and look it up. So I was like, do you have a data book so I can see what these parts are? And Yes, I took a look at the data book and I was like, I could see some applications for these like really cheap, tiny little PIC microcontrollers. I've always been like a hobbyist, putting together all kinds of small embedded systems. I've always been a like personal interest of mine. And so it really resonated, when I saw the data book. So I ended up joining the company. And it's kind of a funny thing. So I joined in 1993 and we take our computers for granted, but believe it or not, Microchip didn't have a laptop or a computer for me at the time. So they were like, do you have a home computer that you can bring in and use? So, so it was pretty scrappy, when I started. Right. So, there was no like, you didn't have any of these, all these corporate networks and all that kind of stuff that we take for granted today. But
yeah, you should do is you should present some kind of like invoice to them like 27 years later with like the accumulated interest on renting your machine over all those years or whatever, how they get stories of like people with AT&T telephones they've been renting for 30 years. So you should present them with an invoice for that.
Yeah, I think that'd be a lot of fun. I'm not sure. I doubt my my corporate finance would pay it, but it would be a very funny thing to send to them for sure. So, but it was a lot of fun. It was so much fun because it's a very small company. The company was maybe $70 million in sales at the time. There was maybe 1,200 employees total, including manufacturing. And the company was a spinoff of General Instruments. So, and the irony, of course, is that, I had many products that had GI, EEPROMs in them. And it turns out that my first computer, which was a TRS-80, it had I apologize. The first computer I programmed was a TRS-80, but the one that I had was a Commodore 64, and it needed this odd interface in order to connect to an industry standard parallel printer. And so I bought this interface, this third-party interface, and later on, after working for Microchip, I was like, I would have done this interface with a PIC. I wonder how they did it. And I took it apart, and it was a GI PIC that was in there, which I found really funny.
That's great.
So anyway, so General Instruments back around 89 or so had decided to spin off their microelectronics division. And that included what is now considered the classic PIC architecture. And it was spun off to a set of venture capitalists. Sequoia Capital was involved in investing in it. They did pretty major management changes, and they spun it off for really like no money. For I think it was like $8 or $10 million, and I think it had
Mm,
roughly about that amount in debt at the time. And so
wow.
GI kind of considered it something that they just wanted to divest themselves of. And
Right.
so the new management team took it
Where's
over, and
GI these days? You know?
yeah, it's a great question. But to a large degree, I think what really helped the company out is that it was a whole new set of leadership that took over. Steve Songi, who is still our president even today, took over the company and really refocused the company on field programmability and, super low cost, one-time programmable at the time technologies. And that's what really opened up the picks for all the hobbyists and a lot of these, high volume embedded control applications, because, the focus rather than on ROM parts, which were really prevalent in those days, was to, come out at prices that, cost points that were very similar to ROM that the customers could actually program instead, eliminate the ROM lead time and the mask ROM charges and things like that. And that really helped the company a lot. And the PIC architecture was very fresh at the time. It was a RISC architecture, single cycle instructions compared to, it was, generation ahead of maybe the more classical 8051s of the time. So I think that helped too.
Yeah. And can you give us a little bit of a feel for that as well? So I came up programming. Well, my my programming is storied and limited in history, but I never really experienced that. That lower cost ROM, and then having the programmability, like you're saying, with the EEPROM and stuff like that. Can you kind of give us a feel for what that was like, and how that was a big shift for people in the field?
If you look at it, historically for embedded designs, maybe in the 80s and early 90s, your only option was really you had these very expensive emulators and they would plug in place of the actual microcontroller. See, we all take like in circuit programming and in circuit debuggers for granted today. But in that day, none of that existed. And so if you went to debug an embedded design, you literally had a dip part and you would plug this massive in circuit debugger in place of the actual device. And then you would start debugging your code. There was typically not C compilers. You're programming in assembly. And then you would sit there and try to, debug your code, get all the code finalized. And then you'd cross your fingers and you'd create a hex file. And then you would send it to the manufacturer and say, I really hope this ROM works. And then you'll get a ROM sample back maybe 6 weeks later, and you plug it in. And what do you do if it doesn't work? Do you pay
Right.
another mask ROM charge? How do you debug it? It was pretty frightful. Now, several vendors eventually, Microchip and Motorola at the time, started applying EEPROM technology. So it wasn't E squared, so it was just electrically erasable. So it was erased through UV light. And so you would have these UV erasable windowed parts that you could purchase, and they were more expensive because of the windows. And then you'd put those in a UV eraser for maybe 30 minutes, and then you would cycle through them, programming them, testing your code out, hoping it worked. If it didn't, then you
Hmm.
try the next one with maybe a code tweak, and then eventually you'd hopefully derive a working code base. And the thing that was a little different was Microchip was really focusing on super low cost EEPROM at the time. And so you could, rather than have to go to ROM, you could just go to production on EEPROMs. And that would save
Uh-huh.
you the risk of basically a ROM part that maybe you've got a code bug in it and you can't, you won't be able to use it, or you have to maybe throw it away. And also the ROM lead times as well. So it was a real game changer at the time.
Yeah, you think about cycle time. I mean, with a ROM, it sounds like that's more akin to hardware in terms of like send out a board, wait for it to come back, all that, build it up, that kind of thing. Versus, I mean, we're like you said, we're spoiled these days. I literally hit recompile, download, and it's ready to go. And that's the instantaneousness of it is. Well, we're seeing that shift now too. I think with a lot of hardware becoming more software-like. Like you think about FPGAs kind of coming up and being able to reconfigure that kind of stuff as well. It really does cycle time increases really just supercharges your development process. But speaking of development processes, I mean, you also alluded to the fact that the PIC was this new risk architecture. Could you give us a context for how that was then different for a lot of people getting into that side of things?
Yeah, it was. So at the time, there really wasn't C compilers. So, today C compilers sort of they distance you from the hardware architecture itself. And so, a lot of programmers today probably are not that familiar with the ISA, the instruction set architecture of the MCU that they're actually programming for. But at that time, the ISA was pretty important because you were writing direct assembly code for it. And there were some fairly unique things. A lot of times, back then we didn't have a ton of peripherals. So a lot of the embedded communication standards were emerging. And so you might want to connect to a access bus or connect to, a I squared C bus or an SM bus, and you may not necessarily have a peripheral that is appropriate for that bus communication. So you'd have to bit bang it. And so, in a lot of cases, when you were writing bit banged code, the timing would be extremely critical. And if you got the timing off, then all of a sudden you might have bus communication errors and things like that. And what was very unique with the PIC at the time is everything was single cycle instructions, and like interrupt latency was exactly 3 instruction cycles. There was no jitter with interrupt latency, and that
Yep.
enabled you to implement bit bang protocols very easily, especially in assembly. But obviously, you can do that in C today as well. But that was a pretty unique proposition at the time, and it's still unique even today. Compared to some other, many other embedded architectures.
Right, right. Well, and I mean, PIC has continued to grow all the way up through PIC 32, which is where we see the modern stuff. What was it when you got started? Was it the I guess I don't know the progression of what the first PIC was numbered with and how the numbering works.
Yeah, yeah. The first pick was called a 16C54 and 16C55. And here's a ironic detail, which is it didn't have interrupts. So imagine programming a part with no
Ooh.
interrupts.
Well,
Which reality is, I will make a comment. I mean, and that is that you had to be a really good programmer to program those parts.
yeah, yeah.
And so to some degree, the code quality was probably fairly high back then, because people had to pay a lot of attention to their resources. And so yeah, the first part was like 512 words of code space and no interrupts. And then over time, obviously, interrupt structures were added. Code spaces expanded dramatically, peripherals expanded dramatically. Everything from comparators to op amps to CAN and USB and just all kind. Every embedded peripheral as it became very popular. Customers may have bit banged it originally, but then typically you end up adding it as a hardware peripheral to kind of automate it, make communication simpler.
Yeah, and so the earliest parts, it was because of cost and because of access to the EEPROM. Are those kind of the things that were making people choose this over other choices of parts?
Yeah, there were some other introductions that happened too. Is Microchip and Atmel was very early to move from EPROMs, field programmable, just one time into flash-based devices. And one thing that was fairly unique to Microchip at the time was introducing an in-circuit debugger. Along with flash technology. It was the 16F 877, which came out around 1997 or so. And Atmel came out with a flash part, the AT90S 1200, around the same time. Although I don't think that part had in-circuit debugging. So the PIC had a kind of a technical advantage there, and that was really one of the predecessors of some of the first low-cost MCU in-circuit debuggers that we all depend on today. SWD and Simsys DAP, and a lot of the modern debuggers that you see today are really, this was kind of the first of that ilk of in-circuit debugging for both flash and setting breakpoints and single stepping and all the features that we take for granted today.
Right. I can't imagine operating without that, but I guess it would have been that same thing where you're pulling. So previous, it would have been you pulled the dip part, like you're saying, you put in a normal debugger and off you go and hope everything goes well, right?
Yeah, yeah. It was actually called an emulator. It was called an in-circuit emulator, and we had
Oh,
this
emulator.
tool
Sorry,
called,
sorry.
yeah, it was called PickMaster of all things, and it was this very massive thing, very
Yeah,
expensive,
yeah.
and pins that you could bend, and then you need adapters in order to get into surface mount, and it was painful to use at the time. But hey, at least you could set a breakpoint and you could single step through your code, and it was a very important tool. But as soon as certain in-circuit debuggers were available, you would abandon that and just move
Right.
on with the in-circuit debugging paradigm.
So, well, speaking of in-circuit debugging, I mean, you had a large part in in-circuit debugging. Is it this one you're talking about, or is it a later one?
Yeah, it was actually this one.
Oh, great. Yeah.
So back in, I'm going to say it was the mid '90s. We were in product development of our first flash devices, specifically the 16F 877. And myself and another FAE, John Andrews is his name. I hope he doesn't mind me using it. And the two of us were chatting back and forth about how it would be just so cool to have a serial in-circuit debugger, instead of just being able to just program the part, but also be able to set breakpoints, and that we could do this with only adding maybe a handful of registers. We came up with a proposal, a spec basically in what hardware registers would be required in order to implement in-circuit debugging on the 16F877. And we did it in detail. So we explained exactly what registers would be required, how they'd be implemented in the ISA, what cause and effects that they would have. And we put together a PowerPoint presentation and then flew to Chandler, Arizona, which is our headquarters, and we met with the silicon design team of the 16F877, and we presented it and we said, look, this is kind of going to be the future of debugging, and nobody's really doing this right now, but it's so compelling that if we just add literally, these, and it was like 30 gates, something like that. We said if we can just
Oh
add
wow,
these
yeah.
30 odd gates into the 877, it's going to enable us to provide tremendous debugging value to customers. And they looked at it and they're like, we just had an issue with the mask, that so we're going to do a redesign anyway. And they're like, this is a good idea. We'll do it. And so they just did it. So they added
That's great.
the support. Yeah, we'll just throw it in there, it won't harm us. And then, and it was pretty interesting because once the registers were there, then we could go to the development tools team, which was implementing MPLAB, what is, I think, historically MPLAB 8 today, and said, hey, we've got this new feature and these new hooks, we need the hardware support now from a debugger side point of view, to be able to support in-circuit debugging. And development tools group originally actually contracted it out to a company in Texas to do the original design, and we later brought that in. So the original, I think, ICD-1 was designed outside of Microchip just to get it out quickly, and then we ended up doing subsequent ICD designs internally from there on in.
This sounds like this is kind of a groundswell, but also like a big shift in like how things were done. Like, what was it that you and John Andrews were like seeing, and like, was it customers were asking for this kind of thing, or was it just a hunch, or what was it that actually inspired this?
Yeah, I remember talking to some customers, certainly, that were talking about their needs. Like they were like, hey, it would be really cool if we could debug. They knew we were coming out with flash devices. And in fact, we already had very small flash devices that were on the market already. The 16F 84 was the part. So it was a combination of like talking to customers in that, and then in them suggesting they wanted some in-circuit debugging. I remember John and I were like, we came up with the aha moment. We just added a breakpoint register and basically a non-maskable interrupt vector, that we could supply all of this. And, we can emulate, we can implement all the communications and software. And so I think it was really visiting to customers and listening to them, and, just listening to lots of customers and debugging stuff on my own, frankly. In other words, like getting
Yeah, yeah, yeah.
frustrated with these plug-in emulators and hating, having to, unplug one thing and having these dip to surface mount adapters. And
And getting the dip pins like actually shoved into your finger. I've done that a couple
of
times.
course, yeah, yeah. In fact, my wife yelled at me one time when she stepped on some of those and her foot was bleeding. So
Oh yeah.
I think it was a matter of myself and John being users and talking to lots of other users, and then just an aha moment. And
Yeah.
frankly, remembering the full trigger of that's a little bit difficult 20 years later, but
Sure, sure, sure.
but it was somewhere along, it was a kind of a combination of talking to lots of people and customers. And I think that's one of the unique things about like an application engineering job, is that it's not just insular. You're not just your own internal company. You're talking to dozens and dozens of different companies and their different perspectives and their needs. And I think that helps you to kind of think a little bit differently, where you're not just thinking corporate all the time and caught in a small box.
Yeah, it is not necessarily as you and I were talking a little bit before the show. Is like there are some jobs where they're more singular and focused, right? If you're like on a product, you're developing that one product, and that's your one thing. But like you said, you're talking to software people internally. You're talking to hardware designers or chip designers internally. Who else do you like interact with as an FAE in general?
Yeah, for me, it's across the whole company. So I'll talk to chip designers in situations where there's a new peripheral that we need, or there's an enhancement to a peripheral that's needed. a good example of that PIC32MZ that came out 4 or 5 years ago. And I worked with a company called Digilent, and they developed a pretty cool product called Open Scope. And it's
Oh yeah, yeah, yeah. We've had Clint Cole on the show a couple years ago now. It was
I actually know
yeah,
Clint very well. He's a great guy.
yeah.
So I worked with a guy named Keith Vogel, who was the lead designer that worked for Clint. And in the development of that, we Keith and Digilent had identified some areas of the ADC, some ADC like nonlinearity performance. There were some problems that they were running into, and there were things that we never really saw because we weren't really stressing the ADC to the same level as they were. So, so I got a chance to meet with, the actual like ADC designer, like, the guy that
Oh,
actually designed the ADC IP and his team, present all the test results that Digilent had collected. And then he ran through all the analog simulations, figured out exactly what the issue was, and then made a Silicon Reb implementation. That's the PIC32 EF versus the EC. So the
wow.
EF has all of those improvements that were discovered on the EC, and then we had to errata the EC, of course.
Hmm.
Actually, it's funny, as an FAE, you'd be surprised how many things you run into that ultimately result in a silicon errata. Where you're
Hmm.
working with a customer and there's some major problem you run into. Now, the vast majority of those are the customer's application, but there's definitely situations where it's a silicon errata, and you reproduce it, and then you work with the silicon designers to fix it in the next rev, and then obviously get it published as an errata as well for other customers to know about it.
Yeah, I've obviously encountered errata. I've dealt with them. I've never had. I've never further. I'm never on like the leading edge. So like, I've never had an FAE be like, oh well, we're gonna have to list this one. But like, what is that conversation like? Like, how thorough do you have to get it to be like, oh well, now this is gonna be an errata?
First off, you have to make sure that you've got to go through the gory details of exactly what's going on. So, you got to get the customer source code. You typically have to get their hardware, and then you've got to put it on a bench, and then you have to cut down the source code to the minimal like size and the minimal functionality, so that you can reproduce what you believe to be the actual errata. So there's a lot of work between the customer and the FAE to kind of isolate the issue to exactly what you believe you're encountering. And then once you have that and you've reproduced it on the bench, then we'll typically pass that on to, we have internal apps engineers, and they're the guys that write the data sheets, and they are also the ones who provide all the like performance and characterization graphs. And then they'll reproduce it. And if they agree that this is definitely a silicon errata, they'll bring in the designers. And then at that
Mm.
point, there'll be a three-way conversation between the module designers, the business unit factory apps engineers, and the field apps engineers. And the three of us will then work forward from there. And then, as soon as will typically first simulate it. So we have really advanced circuit simulation. Yeah, I'm sure most semiconductor
Mm.
companies do. And so we'll actually like completely simulate whatever the issue was, and replicate with the customer's code and everything. And if we
Oh wow.
simulate it, then we can very often like conclusively determine what the root cause is. And as soon as we understand the root cause, then we'll let that customer know, hey, we've replicated it. We understand the root cause. And when we understand the root cause, we can very often determine viable workarounds, because when you understand the root cause, then what the impetus is that's
Hmm.
causing the errata, and then you can figure out different ways that are safe to work around it. And so that customer will typically get that information at that time, and at that point we then verify it, and then it'll go. Then we start writing an errata, and then the erratas can take a little while. They can take a couple weeks before they get published on our website. They have to go through final approval, and engineering
Hmm.
has to sign off on them and stuff like that. But as soon as we really, when we see we verified it, we know that it is definitely an errata and we can prove it, then obviously go to the publication phase, and then we'll typically put that in a queue for a next silicon revision. And that may
Right.
or may
Yeah.
not, when the silicon gets revised, can vary. It depends on when the errata is reported versus when the next silicon revision is scheduled. And some older devices may not have a silicon revision scheduled. So sometimes you have to make a business decision on, really, really older parts if something is reported at that time.
Yeah. 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 Yeah, it's interesting, like, hearing how all this these changes kind of flow through. I mean, the corporation is generally like it's like a machine, right? It's like, there's different functional groups that are doing different tasks, and it's like you can kind of see this packet of information kind of flowing its way through out to the end, which is something someone might read and say, "Oh, I have to do this instruction instead of that instruction," that kind of thing.
That's
It's
exactly
interesting
right. Yeah.
yeah,
Yeah, and the goal is to be totally transparent. So, like, if we find a problem, we want to let our customers know about it so they can work around it.
right.
But on the other hand, you don't want to publish an errata if you don't understand the root cause. So the real effort right up front is to reproduce it. And so you can't just say, oh, this part, the ADC doesn't work. I mean, that's a useless statement.
Right.
I need to know exactly what that circuit is, how you're applying it. I need your source code. Let's sit down and get a scope out, and let's
Mhm.
really reproduce this in detail. And a lot of cases, when we go through that process, we find that there's a customer design issue. There's some other interaction in the system, and it's not an errata at all. And in those cases, the customer is very happy because you now have identified a design issue, and they fix it, and everybody's happy too. So,
Right.
so that's a solution also.
Right. Yeah, I think as as a frustrated younger engineer, I've been like, "Oh, this must be the chip," and yeah, it's usually it's the Chris, not the chip.
That's true for me too. So, I've had it's probably 10 to 1, where 10 times I'll say, it's the device. And I'm ready to go and, write up an errata report. And then I'm like, nope, I made a firmware mistake here. And
Right.
so you got to be careful about these. They don't, they happen, but the vast majority we're not sending these parts out untested. Believe me, there's a
Oh,
massive
sure.
amount of testing that goes on in these modules, and obviously a chip test. And the same is true for field failures too. Another related thing is you have a product that you get a field failure on, and
Mhm.
in a lot of cases it can be an application failure. There's something with the application that maybe there's a calibration issue that the customer hadn't really anticipated, and the part's still operating within spec, but they're getting parts that have a offset or a gain that is maybe 3 or 4 LSBs, and their calibration doesn't compensate for that, but that's within spec of what the device is specified. You
Mhm.
can run into all kinds of issues. A lot of times it's like menial things like crystals don't have the right load capacitors on them, and so the crystal doesn't start up. You get a lot of those, where the
Yep,
customer's
yep.
like, oh, the crystal oscillator doesn't work, and so they send it in for a field failure, and it's not. It's a
Right.
design issue. That's probably the
Yep.
most common one, frankly, is
Oh,
oscillator
really?
startup issues. Yeah, you see it all the time.
Interesting. And that's just because is it because like, they're on the edge and sometimes they do start up on their own without the load capacitance and sometimes they don't?
Yeah, that's exactly it. So a lot of times they're right on the edge, and there's plenty of gain margin in the
Yeah, exactly.
oscillator itself. And so when they prototyped it, everything worked great, and then
Yeah,
and then
right.
they
And then there's some temperature problems and oh, yeah, you have a bunch of them. Yeah.
yeah, and it's usually it's usually a corner case. It's usually like cold
Mhm.
temperature and low voltage, and 1 out of 100,000 don't start up in that circumstance. And so,
Mm.
and we've published dozens of oscillator design app notes to try to help customers through that. But do engineers really read all of the manuals, before they release a product?
I can speak as one engineer and say no. Sadly, no.
Yeah, sadly, that's where the RTFM, the
The
RTFM
moniker
comes.
comes from. Yeah, yeah, yeah.
Exactly.
I mean, so I'm really curious about this kind of customer interaction, and of course, we'll never ask you about which customers you talk to. That's your company's business, whatever. But I am curious, kind of like do you play in certain types of markets? Or I mean, do you see that picks and of the various types kind of fit into different markets in general, or you've probably talked to so many customers. I'm just kind of curious as an overview of the industry.
What's truly amazing, Chris, is that it just covers everything. So, like automotive. So I work
Yeah.
with customers that are doing like, audio system designs and remote
Oh
keyless
yeah.
entry and, ABS systems and ignition systems, fuel injection systems. So, automotive's huge. ADS is a big one
Yeah.
now.
Yeah. What's that?
ADS, it's the automated driver assistance program. So it's all the things like automated braking and It's basically all of the cameras and radar
Hmm.
systems that are on modern cars to be able to do accident avoidance, automatic like
Oh,
cruise
cool.
control automation and automatic braking. If, car slams on the brakes right in front of you and you don't hit your brakes fast enough. And, it's those systems. So that's kind of
Yeah.
one of the new trends in automotive for sure. Automotive's big, but it's a lot of consumer stuff. So it's everything like for example, the Wi-Fi thermostat in my house has a pick in it, for
Oh, yeah.
example, and so there's certain Wi-Fi thermostats that you can buy that are, microchip, a ton, it's all microchip. It's coffee makers, so I actually did the code for some coffee makers that went into volume production, and so it's kind of
Wow.
fun. So I was brewing coffee, with a microchip controlled coffee maker, so that was kind of fun. And it's all over the place. It's like it's hard to see applications that, we're in like TVs, you'll be in like the backlighting. So you'll have like a, PWM controller with the automated backlighting control for different intensities, for higher contrast. It's hard for me to think of applications that we're sort of not involved in, like battery chargers. I got involved with a
Right.
pretty major customer that did standard just double A nickel metal hydride battery chargers. So I got involved in writing the code for that. I got involved with gaming, was really fun. So one of my customers was a pretty major gaming company, and got involved with developing the firmware for all the controls for several of their products. So that was really fun, getting access to all this like gaming software and platforms that didn't exist, in the public domain. And then 6 months later, seeing this stuff get released and in the public starting to enjoy it. So that was pretty satisfying.
Right, right, and then you have an excuse too. You're like, Honey, honey, I'm doing work right now. I'm testing something."
I have to say that was the most bizarre situation to, on business time, play a video game. That was very
Uh-huh.
strange.
Yeah, yeah.
From a moral conflict point of view. But I am really testing it. So
Yeah, right,
but
right.
it's really it's all over the place. I think that's one of the things that made the apps engineering job so much fun, is that it spans so many different products, end customer products, that you just see it everywhere. Just everything I see, I look at it, I'm like, hey, there could be a regulator, an op amp, an MCU in there, an FPGA. Like you kind of see all these products for the components which make up the total system. And
Right.
and then you're in a lot of cases, if you're fortunate, maybe you've engaged with some customers that design that stuff. It's been fun.
Yeah.
Like I've even done like e-bikes. One
Oh,
of my
wow.
customers was involved in doing one of the early, was a pioneer in the e-bike industry. And so I got involved with that. I actually did a teardown of that at ESC a couple of years
Oh,
ago. It was
yeah.
a company called Bionics, and that
Mhm.
was really fun. So I got to explain exactly how their system worked, from an architecture point of view, and demonstrate it. So that was really fun too. So it's a blast.
What about like the fact that you keep saying you're writing code for these customers of yours? I'm always interested in that interplay of like, shouldn't their engineers be writing the code? Like, how does that end up working?
Yeah, well, in the vast majority of situations, the customers write the code, themselves. You're absolutely right. But there's some situations where there's some special IP maybe that the customer needs. So, sometimes there's some firmware IP that they may not have, and we need to develop it. And in which case, someone needs to be assigned to do that. Now, in some cases, the FAE is responsible for doing that, and in certain cases, it had been myself or a different FAE, and it's in some cases the business units will do that. We also get involved with a lot of like third party consultants where they are, we call them design partners, and
Oh, yeah,
they're
yeah.
designed for hire folks. I think you've done some of that kind of work. I'm not entirely sure, but
Yeah, I do consulting, but I've actually seen and I've referenced that list before of the design partners. And it's a great list. It's
exactly.
a it's like by state you can find. And I worked with one of the Ohio based ones when I was living there. Avid was one of the
Oh,
Avid
sure.
Technologies. Yeah, and they were like listed as one. So yeah, and I think some of our past guests have also been design partners.
Yeah, so the normal preference, of course, is the customer write themselves, work through a design partner. But there's always corner cases. There's situations where a customer's like, "Hey, I don't know how to do a special SM bus, command support. Maybe we don't have an
Hmm.
app note for it or something like that." So we'll write that section of code, provide it to the customer, get them up and running. So in most cases, we're not doing the whole design. There's again, it's situational. It depends on,
Yeah.
what the customer needs are, what IP or code is available out in the public domain, or that the customer has the ability to develop. Sometimes the customer doesn't have any software engineers like assigned to that project, and something has to be done very quickly. And it's very good business for the customer and for us. And if that makes sense,
Oh
then
yeah.
we may end up doing that. So it's something you kind of evaluate on a situation by situation basis. And
Yeah, yeah. It sounds like you're like a paratrooper, and as needed, you're like a targeted strike, kind of just drop it in as needed, which is great. I mean,
that's
that's got
right.
to give some like real. Do you have any like really cool examples of that you're able to talk about?
Oh boy.
If not, that's okay.
Yeah, it always gets difficult. I'd have to probably step back and, yeah, it's there's been so many, but I have to be careful about NDAs and stuff like that with
Sure,
those
sure,
customers,
sure.
unfortunately.
No, that's okay.
But yeah, but in a lot of cases, it's there'll be a customer with a very specific problem. I'll describe like a failure analysis one that you might get a kick out of. So, and it
Uh-huh.
relates to test coverage. And so I had a customer that they had a product that was going out to their end customer, and they got a return. They built millions of these, and they got maybe 1 in 1 million or 1 in 2 million they'd get as a return where it didn't work. And so they were like, they send the part back. It was a non-volatile memory in this particular case. We test it and it works perfectly. And we send it back to the customer, and the customer says it fails again in the application. We call those frequent flyers, meaning that the chip flies from our test facility where we run it through all our system tests and goes back to the customer as an NTF, no trouble, no problem found. And then the customer's like, yeah, it's still got a problem. In those cases, someone like myself may end up getting involved. And so, sat down with the design engineers, and I was like, look, I said, you need to get the guys that wrote the code that talk to this non-volatile memory so I can understand exactly how it's used, and then we can write some test code for it. And then we'll connect a very deep logic analyzer to it. And I use one of my favorite tools, the SAIL logic. I don't know if you've ever used that
Oh
tool
yeah,
or
yeah.
not,
Mark and
but
Joe have been on the show before, so
oh, those guys are awesome. Yeah, yeah. In fact, I spoke with both of those guys, and I actually convinced Microchip to resell the SAIL. So I talked to both of those
wow.
guys about Microchip selling it on our Microchip Direct site. So great product.
Yeah.
So I actually went in there with my SAIL, my personal SAIL, and then we did a whole bunch of tests, and it must have been millions of bytes of transitional data. And then
Oh
we
my.
exported it to Excel, and then in Excel we did some very like clever searching, looking at the data patterns, and we could see where the e-squared responded with the wrong data.
Oh wow.
Then we could see exactly like what the bus protocol was that preceded it. And
Oh
and
wow.
as soon as we did that, then we sent the part back and we told the test engineers it's this exact, like, if you hit it with this exact address boundary, with this exact timing, that's when we see it respond with the wrong data. And then the test engineers replicated what we had caught with the SAIL, and sure enough, they could reproduce it. And it was a defect in the part. There was a defect in the address decoder that
Yeah.
was this like third order boundary condition,
Yeah. Wow.
that our test vectors weren't catching. So what we did, we updated our test vectors, and now, of
Yeah.
course, we can catch that type of failure. So that's just kind of an example of a typical, fly in, try to figure out what's going on type of thing.
That is great service, and like the fact that you're digging for that kind of thing is like, man, that sounds like a deep problem. Also, the fact that 1 in 1 million is coming back, that's probably many many millions are being sold as well for that to matter. So like that kind of just boggles my mind in the first place. That like there are, yeah, of course there's companies that need 1 in 1 million to not have a failure. Like that is every single day that happens, and yet you get into these corner cases that are really interesting. Yeah.
Exactly. That's right. And this happened to be an automotive customer. So in automotive, they're generally like you generally are striving for 0 ppm. So
Right.
pretty much
Right.
all
Yep.
automotive customers, if you have a failure, I can assure you it's coming back to you if you supply something to them. So, and you better figure out what the root cause is and put in a corrective action in place. So,
Yeah.
so that was a good example of that. Another really common failure that comes back as an NTF, and I'd like to share that with the embedded community because it's such a common oversight, and that is really proper brownout protection,
Oh
on
yeah.
an MCU circuit. And you would be shocked at how many systems that people will come back where they'll say, "Hey, the flash is corrupted or the E squared is corrupted," and
Hmm.
it'll come in as a the system will brick itself, after it's been in the field
Oh,
for a while,
yeah.
and inevitably, almost every one of those things that I've looked at has been a situation with an improper brownout circuit. And then there's maybe a large holding capacitor in the power supply. And then power goes away. And then the MCU ends up browning out and it's sitting at some voltage like a volt and a half or 1.2
Mm,
volts. It's well below the VDD min, but
yep.
it's allowed to execute code. Like it's actually allowed to keep running code,
Right.
and
Right.
you're talking about the Russian roulette now. What's going to
Hmm.
happen? Where does the PC
Yeah.
land? And then
Right.
the power comes back up and it doesn't get a reset 100%, and then boom, it does a write to its flash, and now the flash is corrupted. and
Yep.
and
Yeah.
there's tons of ways to mitigate that, and totally prevent that from occurring in a system. And
Yeah.
but that's probably the most common, what I call those will be frequent flyer, but they're really not a defect in the silicon, but a system design problem that can be
Yeah.
easily rectified.
That brings up an interesting point too of like there are I was really surprised that Microchip kind of ended up branching out into so many other components that are outside of microcontrollers that like I first learned of the company and I didn't quite understand the scope of the product portfolio, but there are like other things that are out there that could actually assist in something like a brownout detection and stuff like that. When I first started with the company, I didn't actually understand the analog portfolio as well.
So probably, I'm going to say in the late 90s, 98ish or so, we started a analog products group. It was headed up by a fellow named Rich Simonsek. He runs it. And the idea there was that we had customers that we looked at their designs and like, yeah, they're using a PIC, but then we're like, hey, they need an op amp or they need a proper brownout reset circuit, like we were just talking about, a CPU supervisor or maybe a regulator. And it's like, hey, we have all the process technology and we're doing all those types of mixed signal analog designs anyway for the MCUs, so why not branch into
Right.
that, because we can service those sockets for the customers as well. So there was a huge investment in diversifying, beyond just microcontrollers. And I think today roughly microcontrollers are about half of Microchip's total revenue, and the other
Oh
half is
wow.
non-microcontrollers, is something analog or FPGAs or PCIe controllers through various company acquisitions.
Did you guys buy
It was Microsemi. It was
Microsemi? Okay, that's what I
yeah,
meant.
it
Yeah.
was Microsemi about 2 years ago, and that
Oh,
was
cool.
of course Actel actually.
Mm.
So all the Polar Fire and series of FPGAs. So it's a good strategy from a just from an overall diversification. But what's cool about it is like the MCU vendors, the guys that are building PICs and AVRs, they are still like laser focused on their business. Like they run
Yeah.
as
Yep.
independent companies, profit and loss and all that kind of stuff.
Sure. Sure.
So it's good. It's almost like you just become a larger, you have a larger array of products that you can offer. And but it doesn't prevent you from continuing to have the same kind of laser focus on micros and the traditional PIC and AVR businesses.
Yeah. How does that end up impacting you? Do you have to learn more now, like of all the FPGAs and stuff like that, and cover more stuff?
Yeah, that's actually had a big impact. So, probably 4 or 5 years ago, we started what are called specialist areas for FAEs, and we currently have 13 specialist definitions within Microchip, and one of them is FPGAs, just as you've outlined. And
Yeah. Okay.
so, I personally am an MCU specialist myself, and so I tend to focus on all the PIC32s and SAMs, AVRs, regular PICs, and all the development tools associated with those. We have analog specialists that are focused on op amps and high speed ADCs and DACs and digital pots and that product line, and power specialists for doing power supply designs, switch mode power supplies, boosts and bucks, and various reference designs in that area. Wireless, for Wi-Fi, Bluetooth
Oh yeah. Right.
types of
Right.
designs, and wired for like CAN and Ethernet. And security is huge these days. We have FAEs that are entirely assigned to security, so all the authentication for
Oh yeah. That
AWS. And
the ATEC chip. I've written
that's
about that once
exactly it.
before.
Yeah, the
Yeah.
ATC. Yeah, those parts are. We've sold 1 billion of those, if you can imagine that.
Whoa.
Yeah.
Could you explain what that
So
is for people who haven't heard of that?
Yeah, there's a whole series of parts. There's a ATC. It starts at 204, and then there's their most recent one is the 608. And we have some new parts that we have not announced yet in that family. They'll be coming out later this year. But what they're all about is they're these ultra secure, trusted devices that you can you place keys and potentially authentication codes and certificates inside of them. And the hardware is designed in a way that that makes them highly secure to attacks, both physical and obviously electrical attacks. One of the challenges you
Yeah.
have with a lot of MCUs is that with all the different test modes and things like that, there's people that are always trying to attack those platforms, electrically
Right.
and mechanically, to try to reveal security keys.
Right. Yeah, you don't just write your keys in the code and they get dumped out, and then it's like, oh look, there they are.
Yeah, yeah, and you see those hacks all the time for all
Yeah.
kinds of
Yeah.
different MCU
Oh yeah.
vendors across the board. And what the customer ends up doing is we have a secure facility that we can program those and then ship them to the customers. So the customers, they don't have to worry about the keys being lost or potentially copied by a subcontractor that might be building their boards. That's a whole
Yeah.
nother
Yeah.
thing.
Oh
So
yeah. Yeah.
there's a better manifest in keeping track of who knows about your keys. And so
Yeah.
they're pretty good. And we'll do versions of those that are like automatically registered with like AWS and the Google Cloud services, so that so if you're building a product that's going into AWS, it can just be pre-provisioned automatically, and you just stick one of these parts into it, and it'll automatically provision itself for AWS Cloud. And it just
Yeah.
simplifies the whole key exchange and the whole authentication process for customers.
Right. Well, and if everything online these days, it's big, big money, big important things to be making sure your devices are secure.
It is, yeah, yeah. It's a huge growth area for us. That's not my personal protection area of expertise. There's
Mhm.
a guy Dan Uvari's kind of he's my counterpart. That's the security expert, so he'd be a good one to maybe interview in the future if you wanted to discuss security.
Yeah, yeah, yeah. We've definitely talked to some of the people that have been doing some of the attacks on the chips, so it'd be good to hear it from the other side.
Absolutely.
uh, So to go back to the specialization side of things, so you said you obviously you do the PIC 32 and a lot of the microcontrollers and things like that, but you've also written app notes, and I've always been curious about that. We've had some other people that have written app notes on here. Could you kind of run us through some of the ones you've written and what kind of what some of the knowledge people might be able to get if they dig into those?
Yeah, sure. So probably one of the most recent one is a Harmony reference design that I co-authored with Tim Friend, and Microchip introduced an entire new software framework for PIC32 called Harmony. It was Harmony
Hmm.
1, Harmony 2, and now it's Harmony version 3 that was most recently released. And Tim, myself, and our customers were like, "Hey, this framework's pretty complex. How do we get up to speed? In understanding the APIs and the proper way to interface with the drivers and what the callback structure is like." And so I was pretty inspired by some of these RGB LED cubes that were kind of coming out around circa 2014, I think it was. And
Uh huh.
so Tim and I decided to design our own RGB cube and build the whole thing on Harmony with a PIC 32. And so the two of us went pretty crazy, and we implemented tons of scenes, and we have a USB bootloader in it, and we have Bluetooth. We even went so far as adding Bluetooth to it so you can control the cube with your phone. And just we went absolutely nuts with Harmony. And then we gave it back to Microchip and published a app note. So if you go to microchip.com/ledcube, you'll see every aspect to it, all the source code for that, and that's all the Harmony APIs for everything, implementing the special SPI interface with DMA controllers for doing all the LED matrix updates. It's all done in hardware, to the USB interface for the Bluetooth interface, all that kind of stuff. So that's the most recent one that I published with Tim. Some kind of fun ones. Did an app note on ICSP calibration, which is where an MCU is in a system and in final test, and then it determines that it needs calibration parameters, and it send those to external MCU that grabs those, and then that MCU implements the ICSP protocol, the in-circuit serial programming protocol, and then programs those parameters back into the test device.
Huh.
So it's kind of a way of, you could do this with E squared, like you could write it to E squared or write it to Flash, but this gives you kind of a permanent, it's done through the ICSP interface. So it can go straight into program memory, and you can eliminate like the self-write instructions to Flash in that situation as well. Did a DTMF generator, this was back in the days when we were doing a lot of the old POTS, dialing types of systems, which you don't really see much these days, but it was a technique of implementing DTMF in code, implementing a
Oh,
D-data converter.
POTS is a telephone system. Is that right?
Yeah, plain old telephone service. Yeah.
Oh, okay, okay.
So it was very obviously had DTMF dialers, and there was a lot of products that like security systems and stuff like that would want to be able to pull dial tone and then be able to DTMF dial a service, and then potentially through DTMF send a status code, maybe what door has been violated, and that type of thing.
Oh, cool. It sounds like an app note like that would be kind of like a timepiece for what it is as well, but it's like the underlying like theory that you're talking through and the actual circuitry, that stuff finds use in lots of other places too. So that's a really cool idea to look at.
Yeah, it's funny. Like the R2R ladder from that app note, that is actually implemented in open scope.
Oh, cool.
So when I was talking to the designer, Keith Vogel, about the open scope project, then I showed him that app note and talked to him about that. And he ended up implementing it in open scope for the DAC,
Yeah,
it's the waveform generator is implemented based on that app note, which is kind of cool.
yeah.
Did a piecewise linear interpolation, which is situations where you have like a nonlinear sensor. So you may have encountered some of this kind of stuff with Keithley, where you have a sensor that has maybe a very nonlinear analog output
Yep, yep.
voltage, and then you want to compensate and provide maybe a direct linear output to your customer. And so there's a couple ways to handle that. A very most basic example of that is like a PTC, a standard
Yep, yep.
thermistor, which and it's like a third order polynomial equation that you can write that in code if you want to. But this app notes implements what's called piecewise linear interpolation, which is where you implement a fixed x and y value, and then you do a linear interpolation between those two. So it's not
hmm
quite as accurate, but the CPU required for it is much lower, and it's much smaller in code space. So
I was gonna say it is appended by the PIC 12, 14, and 16 series. So it's not like you're not throwing some kind of like monster microcontroller at the problem.
yeah.
You're getting in, getting done. You know.
Exactly. Yeah, these are for very small, maybe more resource constrained applications, and yeah. So it's I also did like a clock, a couple of clock designs, LED multiplexing, that type of thing that are published as well. So
That's cool. Like, how long does it take to write an app note like that? I mean, is it years, months, weeks? I don't actually have an idea.
yeah, it's usually the process is it depends on how complex the app node is. Like the LED Cube project, Tim and I worked on for over a year developing that, so that one was over a year. Yeah, because of course, we have a full-time job too, so it's not like we're just writing an
Yeah.
app note just for the fun of it, or during our regular business hours. Some of the other ones that are simpler maybe took a month or a couple of months. So you write them, and then you'll send them in for review. They have to get reviewed by apps engineers for correctness, technical correctness. Someone else has to test the code, make sure it actually works. There's obviously a cycle of feedback. You put the document in for a technical feedback review, and typically you'll assign somewhere between 3 and 5 people as technical reviewers, and then they'll put all their comments in, and then you'll
Mm,
review all of that. You'll make a final publication, and then that gets sent out for publication at that point.
yeah. Yeah, I never really put it I mean, the way you explained it there, it says, I never really put it together before, but like it is almost like a journal entry or journal article, I suppose, that like the science community kind of does in the fact that there's feedback. It's just you don't usually see it from independent entities so much as you see it from, companies usually around a chip or a concept to promote, not even to promote, but just to help explain things.
Yeah, yeah. I mean, in a lot of cases, we were writing app notes where we had a specific problem that customers would run into, and we want to be able to supply, some code and maybe some, some text schematics, things like that as a solution to that. Things have changed a lot with app notes. Like,
Hmm.
nowadays, people are expecting, code configuration tools, or code composition
Yeah.
tools. And, so I think that's changed a lot. If you look at, from Microchip, there's two different tools: MCC, the MP Lab code configurator, and then there's also MHC, the micro Harmony configurator tool. And those encompass a lot of what might have been app notes years ago. So those will have, peripheral setup and, drivers and, all kinds of configuration like graphic stacks and things like that. That,
Yeah. Yeah.
you might have had an app note with, a huge zip file and source code that would, maybe provide an example of how to do a VGA graphics design. And, with these code composition tools, you'll instead, configure this as with the specific display that you're planning to use, and, the graphics library that you're planning to use, and then it'll just put all of those parameters, header files, all the source files
Oh
and
wow.
everything into your project, and it's already pre-configured. So I think the app note phase has changed a little bit. Still a lot of cases where app notes make a lot of sense for sure, especially in the
Hmm.
hardware domain. But some of the areas, the app notes have been, I think, superseded by some of the content generation tools that are out these days.
Yeah. How about your personal workflow? I mean, do you find yourself using them like in personal projects, or is it
Oh,
more like, well,
yeah, oh, tons. Yeah, yeah. I've done dozens of different microchip designs, and I find that the best way to really learn the parts, especially if you're going to support them, it's kind of foolish to go to a customer and say, "Hey, I'm going to try to solve your problem, but I've never used the part before."
oh,
You
that's
know,
true. Yeah.
so so one of the things you're just constantly doing is, as we come out with new devices and, new software stacks, like Harmony H3, for example, is to do a personal project with those. And so I'm always assigning myself, a personal project to learn new technologies. I mentioned the LED cube that Tim and I used to learn Harmony H2. Like, back when we started coming out with a bunch of like switch mode power supply peripherals on PICs, where we could do boost
Mhm.
and buck converters and stuff like that. I didn't have a lot of experience with designing switch mode power supplies, and so I was like, well, those Nixie tubes are kind of cool. I think I'll build a Nixie tube clock, and I'll do the whole thing, with a MCU with switch mode power supply. And so I went and built one. And at the time,
Nice.
we were actually coming out with a Ethernet stack, an embedded Ethernet stack. And I was like, well, wouldn't it be cool if I had a Nixie tube clock that was also connected to the net, and so it got the time from the network time server, so I don't even have to set it. And wouldn't it be even cooler if it showed the microchip stock price on the Nixie tubes in real time? That'd be kind of cool too.
Yeah.
And I live in New England, so we have like really violent weather in this area. So maybe it would be a cool thing to have, I don't know, weather reports on the Nixie tube clock too. So
John, it sounds like yeah, you have your own feature creep kind of going in here.
yeah, yeah, I'm sure there's no one on your show that has ever
Right,
experienced
right,
feature
right.
creep before, but that
Right.
project absolutely did, and it was
Yeah.
really really fun though. So that was a really fun project. Kind of learn the TCP/IP stack, and some of the different cloud services that were out there. I used the Yahoo APIs, which were pretty cool at the time.
Yeah. Yeah. Yeah.
Use one of the early cloud services, Cosm, that provided cloud configuration type stuff, and you could get JSON strings back, and you could auto configure things like your location and the stocks that you wanted to display and all that kind of stuff, with your phone,
Yeah.
on the Cosm site. It was really fun, very very educational. Done a lot of other different projects. I'm big into pinball, so that's just kind of a personal hobby. And there's been a lot of microchip pinball type of aftermarket boards and open source projects that I've been involved in implementing the last few years.
Yeah. So the things I know about pinball, I know about pinball because of Parker over on the Macrofab Engineering podcast also talks about pinball a lot. And then I know it from listening to Ben Heck talk about it and Jerry Ellsworth. That's pretty much, oh, no, sorry, Jeff Kaiser as well as another guest of the show who's talked about it a lot. But that's basically my exposure to it. And I know that it takes a lot of current to drive a pinball machine. That's about where I stop.
You should
Yeah.
play, or you should get involved. It's a total blast. In fact,
Oh, I love playing, but I just don't. I've never had one. I've never wanted to rebuild one. I don't have space for one. That's kind of the big thing
Uh,
too. So
you can always have space. So let me tell you my first pinball machine. Okay,
okay,
so I was in college, dorm room. Okay, and my roommate was a mechanical engineer, and he designed a loft that lifted both beds off of the ground so that we could
nice,
fit a pinball machine into our dorm room. So I've owned one since the college days. It was a Gottlieb Genie,
nice.
and so what's interesting is of that generation of machine they had these ancient MPUs in them, and they were running on Rockwell 4-bit microcontrollers, and there
Oh,
were there were
nice,
there
nice.
were three of them, if you can imagine that, with ROM code. Remember we talked about ROM and all that
Yeah,
kind of
yeah,
stuff,
yeah.
and unfortunately, all of these things have batteries in them, which are like the bane of these machines, and because
What?
the batteries ultimately leak. So they leak base. Everybody say it's
Sure.
battery acid, but it's not actually acid. It's the inverse of that. And, it's a caustic base
Is that just to
material.
get like a nice like? Are they just like rectifying the AC input or something, and then using that as like?
It's to retain settings. So it's to retain like high
Oh, I
score
see.
and all of the operator settings, like it costs 25 cents for 2 games or that type of
I
thing.
see.
Those
I
settings were
see.
stored in batteries, in basically battery backed up memory,
Uh huh.
RAM, so that when this game is off, it can remember all those things when you turn the game back on. But the batteries ultimately, they every one of them leaks and it destroys the MPU, and you can't get any of
Okay.
these components anymore. So it's just impossible. And a guy in Germany, Ralph Thien, super cool guy, he took a open source project called MAME. It's called Modular Arcade Machine Emulator. I don't know if you're familiar with MAME at all, but
Yeah, yeah.
you can play video games. All the classic video games are supported on MAME, and in the last maybe 5-6 years, there's whole pinball machines that are implemented in MAME as well. And if you're not familiar with emulators, these things are fascinating. So they actually implemented the entire logic of the original MPUs, and they implement all those in software, and they run the original ROMs. So the original
Mm.
actual ROM that the games had, and they operate the game faithfully as the game was
Mm.
originally programmed with the original bugs and everything. It's pretty cool.
Yeah.
So Ralph ported PinMame to Raspberry Pi running Linux, and then he used three of the Microchip PIC-18 microcontrollers, and they provide all the real-time I/O. So, and they sit on an I2C bus of the Raspberry Pi, and so one of the PICs is a display multiplexer, so it's doing all the they're all fluorescent displays, vacuum for VFDs,
Oh yeah.
and
Yep.
then another one handles all of the solenoid drive and lamp driving, and then the third one is doing all of the multiplexing, scanning the switches, and so they all sit on a common I2C bus and report back data. And that's been like so satisfying to take something that it's got this 40-year-old rotted MPU, and the thing is dead, and
Yeah.
then plug in a Raspberry Pi with three PIC-18s, and then it comes to life and it's running the exact original game ROM software. And by the way, it's Wi-Fi, so it's got a web server on it, and I can
Right. Of
control
course.
everything on my
Right.
phone, and I can do firmware updates from Germany while I'm sitting here in Massachusetts. So it's pretty cool stuff, so that's been a blast.
The PIC 18s, they actually talk. Do they have like solenoid drivers then on the I/O output? Is that kind of the idea, or?
That's a great question. So, on the architecture of these games, is they typically have like the equivalent. Their older parts are like 6305s, but they're equivalent to like TIP 102s. If you're familiar with TIP
Uh huh.
102s, they're sort of like that. So they have 60-volt, 100 volts, anywhere between 5 amp and 15 amp. Typically Darlington transistors. So
Yeah.
they'll have a whole array of those on what's called the driver board, and then they'll be typically on these older games, it's a 4-bit bus. So there's a 4-bit data bus. It's basically 4-bit latches. And then you have separate latch assertion signals that are available
Hmm.
for each one of those sets of latches. So you might have maybe 20 latches if you have, 80 outputs. And
Uh
there
huh.
may be, of which those 80 outputs might have maybe 20 of those are high current solenoid, and the remaining 60 are lamp drivers. They're just driving little
Yeah.
incandescent lamps. So the PIC is dealing with getting the data formatted in the appropriate 4-bit bus and generating all the appropriate latch signals to get all the data out there. And then it has to deal with timing because, like, when you hit a solenoid, you've got to turn it on, but you have to turn it off if you don't turn it off, it'll smoke and possibly
Right.
catch
Yep.
fire. So,
Yeah.
so you got to, manage all that kind of stuff too.
Mm. And so you're saying previously the Rockwell 4-bit processor was that directly driving those? I guess it wasn't directly driving but they were driving the Darlington, the tip one and
No,
twos.
no, they just like the PICs went
Uh huh.
to the 4-bit latches, and then the
Oh,
4-bit
okay, okay,
latches are ultimately driving the drivers. So,
okay,
so,
okay.
so they were on separate boards, which made this quite a bit more convenient. So you had a
Mm.
larger MPU board. You have obviously a power supply, of course, and that was all linear and provides plus 5 volts.
Many amps.
Yeah, and the power supply actually had to do things like minus 12 because,
Yeah,
the
yeah.
EPROMs of those days were not single voltage. So the power supply
Mm.
had plus 12, minus 12, plus 5, all that stuff going into the MPU. These are all things you take for granted today. You think, we're used to
Yeah.
single voltage systems, but back then it wasn't like that. And then it's got these 4-bit Rockwells, and it's got EPROMs and ROM and just full of stuff. And then from there, some of its IO expanders. We're also used to MCUs where, like, they have IO ports, but back then it was a microprocessor, and you'd have to have something called a
Mm.
PIA, which is a peripheral IO expander. And so it would be another chip that would be sitting on the microprocessor bus, and it would contain like a latch signal and direction control, and then it would have a register for the output bits, the equivalent to like a tris or port registers that you might have on a PIC. Those
Mhm.
things are in a microcontroller, but back then in that particular architecture, it would be in a separate IO a PIA, peripheral IO
Mhm.
expander or adapter. So
Yeah, yeah.
it's pretty cool
Huh.
stuff, but it would interface
Yeah.
in the same manner. So it just really took it eliminated the Rockwell and that architecture, and then interfaced to the driver board in exactly the same way.
Yeah. I guess what I was wondering there too is the rock you said there's multiple Rockwells, like, who was the ultimate master of that system?
Oh, that's a great, great question. So there was an ultimate, and you're absolutely correct about that. So there was one Rockwell that dealt with all the displays, because the problem is these were multiplex displays. So you had anywhere at least 5 displays. So there were 5, 6-digit, 7-segment displays. But obviously, from an I/O point of view, they didn't want to do 7 times 6, 42 times 5. They didn't want to do 200 wires in order to connect between the MPU and the display, so they multiplexed it. And it turns out that with these VFD displays, you have to multiplex them at a pretty high rate, and you can't screw it up. Like, if you keep one
Yeah, yeah.
segment on, even for an extra microsecond or two, your eye will pick it up. You'll see a bright segment,
Oh.
and you can
Oh,
potentially
wow.
burn it out too. So they had a separate Rockwell microcontroller that dealt with just the displays alone, that was just taking care of all the multiplexing. And then they had one that
Mhm.
was doing all the, like, solenoid timing and that type of thing, and switch scanning. And then they had a main MCU that was running the game code. And they had sort of some of this is not in the public domain, so it's been kind of reverse engineered. But
Mhm.
it's my understanding is that they had built sort of a mini operating system with some kind of standard sort of game like commands that was running in the general ROM. So that's why they
Yeah.
had 3 different MPU or MCUs that were running in that system.
Yeah, yeah. I'm always interested too, like with the retro gaming kind of community too. It's interesting how like the purists who are like, oh no no, but we have to have the exact firmware as well. It's sometimes it seems like it would be simpler to just go reverse engineer the whole thing, but it sounds like there's actually not even much interest in doing that because you want to have that same experience.
Yeah, there's pluses and minuses. There's a company called Neewumph, and the guy's name is Dave Humphrey. Great guy. I know him personally, and he's just re-implemented all of the game code. So his approach is not to emulate anything. So he's just
Mm,
like
got it.
he just rewrote everything from scratch, and he used a pick on some of the original boards. I think he's got an ARM part on some of the newer ones that he has out now. So that was his approach, and there's some significant advantages to that approach because now you can add new features. If there are bugs in the game, you can fix them, and you can make the game even more interesting.
Yeah.
So there's definitely some advantages to taking that approach. But there's some downsides because you can introduce bugs too inadvertently.
Of course. Yeah. Yeah.
Because you're writing this stuff from scratch. So it's like everything. I mean, the cool thing about the MAME approach is that you're guaranteed to get exactly how the game was originally, and you know that firmware was pretty well tested probably before the game was released. So
Right.
it does give you that. And there's another one which is called Mission Pinball Framework (MPF), and I'm pretty sure Ben has done some extensive work with that. And with MPF, it is a base framework that you can write all your own game rules with, and it's written in Python. So you can write all of your own game rules all in Python running on MPF. And that is actually supported on this same Lissy board that I'm using. So I could run the original game ROMs if I want to with PinMame or with MPF, could write my own game ROMs. And I have a friend that's currently doing a Harlem Globetrotters where he's doing his own game development,
Oh.
and another friend that designed his own custom pinball machine. And I think Ben did his
Oh.
own
Wow.
custom machine,
Yeah.
if I remember correctly. I remember watching a couple of his YouTube videos on it,
Yep.
and
Yep.
uh, and I have a local friend that did something very similar to Ben, and he used MPF for his game also. Really impressive.
Yeah, yeah, definitely. Yeah, and that's the thing. Like until someone like flips open the actual game board, or what's it called, the deck or whatever the board is called,
The playfield, yeah,
playfield.
playfield.
Yeah, until you like flip that open, you're like, oh, well, there's not much there, and then it's open up. You're like, oh my goodness.
Yeah, yeah. There's a
Yeah,
lot
there's a
going
lot
on
going
in
on.
these things. Yeah, there
Yeah.
really is, and it's really fun. If I'll share a personal story. When I was a kid, I always wanted to be an electrical engineer. Probably since I was maybe 6 or 7 years old. I saw
Wow.
my first electronics, and it was actually my brother. You'll get a kick out of this. So my brother, he's actually an electrical engineer too. He's 5 years older than I am, and
Nice.
he came home with a school project, like a science project, and it had 20 nails in it and a battery and a lamp. And it
Uh
had a
huh.
question, 10 questions on the left side and 10 answers on the right side. And you took these two probes and then you'd put one probe on the question, and whichever was the correct answer would complete the circuit and the light would light up. And I was
Nice.
fascinated. I'm like, how is that light lighting up? How does it know which one's the right one? And so
Right.
so I was just fascinated by it, and then and pinball was big in the '70s. I was growing up in the '70s, and so you go to even like you went to the equivalent to a Walmart. There was a store
Hmm.
called Zares where I grew up that was kind of like the local Walmart, and they would have pinball machines there, believe it or not,
Oh yeah.
and so. They would break all the time because they were electromechanical, and they'd have technicians fixing them. And if there was like a machine open, I would just be immediately drawn to it. And I would just be, I couldn't get away from it. I would be staring everything down. I'd be talking to the technician. I'm sure that these guys were so annoyed by me. And I would ask
No,
him a
they probably loved
million.
it. They
I
probably
think they
love. I mean,
did. I mean,
they were you when they were younger. It's just a different
that,
system. It was someone fixing a
yeah,
TV instead of a pinball machine. You know what I mean? Like it's
yeah,
the green, the just that keeps circling around. It keeps circling around, John. You know, and now
yeah.
people are listening to you, and this is going to cause more people. So yeah, it's the circle of life.
Yeah, I hope you're right. I hope you're right. But it totally inspired me. And so I was
Yeah,
probably maybe 8, 9 years old, and saw the inside of my first pinball machine, and I was just like, "Oh my god, this is fascinating! How does it work?
yeah,
The mechanicals of it, all the electronics. They were entirely mechanical then. But a few years later, the first solid state games came out, and I was just totally hooked. And
yeah,
then the
yeah,
TRS-80 came out, the original Apple One, and then I get told that the Commodore 64, and I was just
yep,
totally hooked by
yep.
the computer
Never coming back
revolution at
from
the
that one.
time. Yeah, absolutely. So it was really really fun. So I even made my own pinball machines.
Oh,
So
you
when I
did.
was a
I
kid,
was gonna ask if
yeah.
there was
So
like an early like when you're like 10, you tried to make one, and
yeah, yeah, it was really fun. So my parents had gotten they redid the kitchen, so there were all these like cabinets sitting around the basement, and I was like, "Hey, Dad, do you mind if I like do something with these?" He goes, "Yeah, sure." And my parents were pretty. They allowed me to use power tools and everything when I was like 10 years
yeah,
old. So I do think, I mean, again, for me, the lack of caution was great because I just, I learned, if I cut something, I
yeah,
didn't do it again, and
yep,
so,
yep.
grabbed the circular saw and and drills and all that kind of stuff, and made my own pinball machine. Used a calculator and some rubber bands and some nails and coat hangers to make the flippers, and
Oh,
the thing was
nice.
totally playable, and you could score
That's
and
awesome.
everything. It was really crazy. So so it was really fun. I was maybe, I don't know, maybe 10 years old at that time, or 11 or something like that.
Yeah.
So I think it's really I think it sort of put me in kind of sent me in this direction from a career point of view. It certainly inspired me at
Yeah.
minimum, and to kind of loop it all together. I was on a hunt to find the first pinball machine I ever played. It was a
Uh-huh.
1973 Gottlieb Kingpin, and I found one about 2 years ago or 3 years ago. It was a disaster, completely rotted, just a total mess. And I did 100% restoration on it, rebuilt all the cabinet and totally restored it. And I played all the time. So it's really fun.
I have to ask how many is it like you walked out in your basement and you have like a whole museum down there, or are you a more selective a gatherer of pinball machines?
Yeah, the collection changes all the time because I have all these
Oh, it
friends that
does.
keep
Yeah.
like bringing games over for us to restore together. So, so the collection changes pretty radically, pretty often. So I have quite a few in the basement these days. I'd have to. It's hard to keep track of how many are there. If you're a pinball collector, you will find that they tend to get out of control as time goes on. You tend to have more and more. So, but it's all a lot of fun. I have a big wood shop in the basement too, so I do a lot of woodworking for fun as well.
Yeah, I've heard that. Yeah, when your friends start to hear that you're interested in one, then they just keep coming. So, like a lot of wounded soldiers, kind of show up at your door.
Yeah, yeah. Like I like to call my house the Gottlieb Spa. So it's the place that these tired games come to be rejuvenated. And
Right. It's like that the toy collector in the Toy Story 2 where they redoes or Toy Story 3 where he redoes Woody and he, fixes him up and stuff like that.
Yeah, yeah. I find it very therapeutic. It's just it's a great hobby for me, and my friends really appreciate it, and we all really appreciate getting the games, and I think it's a good tribute to to the original designers of these games. Keep these things alive because they were incredibly well engineered and incredible. And
Yeah.
what blows my mind is how you can make such a complex machine with no microprocessor, entirely with electromechanical. I'm talking all you have is relays and steppers and solenoids, and that's it. And how are you going to keep track of what current player is there and the score, and how do you deal with carrying, and how do you reset it all to zero, and
Mhm.
how do you deal with resetting the drop targets when they're all down, and how do you know when that's going to happen? And it's unbelievable. It's just so
Yeah.
clever, and it's all relay logic. So it's not code, it's a schematic. So you stare it down and you're like following, you're tracing everything through each relay contact to try to identify where the problem may occur. And then you're there with LEDs and, alligator clips and trying to diagnose it and figure out what the issue is. And it's really fun. It's cool.
I really like this contrast too. This is like the technical fellow from Microchip who goes home and is like, no more microcontrollers for the next couple hours. I'm woodshop and I'm relay logic. It's like a really good contrast. I really like that.
Yeah, I love the contrast. I think it's
Yeah.
very important in life to have things that balance you. And so, so I think it's really good to leave the high tech stuff behind at times and just do something
Yeah.
totally different. So it's
Yeah.
really a lot
Yeah.
of fun. It's great. Yeah, great observation.
And you have fun with it too. You've now been on a. This is not your first podcast appearance. You have been on a classic pinball podcast, so people can listen to that. Yeah,
Yeah, that's right. Yeah, my buddy George and Dave. It's on Doctor Pinball Dave Restorations, and he's one of my friends. He lives really local to me, and he professionally restores pinball machines. And he and his buddy George, they started a podcast about 6 months ago or so on classic pinball machines. I think they've done 12 episodes maybe so far, and I've been on two or three of them as a guest
that's
speaker.
awesome.
So that'll
Yeah,
be
yeah,
fun. And at some point, they're gonna come to my house, and we'll do an entire episode on my collection. So that's in the near term plans.
that's good. That's a good teaser for later. John, what else should we know about your? To switch back to the professional real quick, is there anything else we should know about your microchip days or even pinball days? I mean, anything else you'd like the audience to know about you?
Yeah, well, I'll tell some crazy stories that I think everybody will get a kick out of.
Great, sure, sure.
Many years ago, I was traveling with a sales representative, and we have dinner, and then he's like, "Hey, I've got one more customer I want you to meet." And I'm like, "Really?" It's like 7:30 at night, and we drive to this like fairly seedy section of town, and we go into this bar or whatever, and this guy shows up with a suitcase, and he's in like a trench coat. And I'm not kidding. You can't make this stuff
Yeah,
up.
no, no. I'm trying to. I'm like playing this forward in my head. I'm like, I think I've seen this television episode, but I'm trying to figure it out if it's like if it's gonna be Law and Order and like something bad happens, or if it's more like like a joke TV kind of fun thing.
Yeah, yeah, it was really crazy stuff. And so he opens up his briefcase, and he's got a cable TV descrambler. So back like
Oh,
20 years ago or so, there used to be cable TV was analog, and
yeah.
if you didn't pay for your channels, they would scramble there was like a video sync pulse that would be like suppressed periodically, and it would cause the TV to scramble, and you couldn't watch it. And he had this cable TV decoder, which was entirely illegal, by the way, and it had a
Yeah.
microchip pick on it in it. And
Ugh.
he points to it. Can you produce this for me? And I put up my hands. I'm like, look, I'm like, I cannot reverse engineer this. I can't have anything to do with that. That's not what we do. I said, however,
Yeah.
if you want to build your own thing with your own spec, I can put you in touch with, a consultant, one of our design partners that can help you out. And he goes, I have cash. And he has cash with him. He's like, if you could do this. And I was like, nope, I'm not having anything to do with this, and, but I'll
I
get you in
mean,
touch with one of my design partners. And, it was crazy. And he
you
did
could have
end
you
up
could have
hiring.
taken a turn towards a life of crime right there. You
I
could have
could
been a
have,
totally different
yeah,
path.
yeah, yeah. I would be out. I'd be.
A different type of kingpin. Not
That's
necessarily a
right.
pinball kingpin.
Yeah, yeah. That would be. I'm so glad I chose not to go down that path, and so
That's
that was
right.
pretty crazy. And then he walked. He did. I did end up hooking up with a design partner. He did ultimately end up. The design partner did design for him. He bought like 100,000 units, so he did end up
Oh
building a
wow.
bunch of these things in the end, which is kind of cool. But so he was pretty serious. But another one, I'll tell you another call, which was really crazy, was had an automotive customer that was in a very bad area of New Haven, Connecticut, and
Hmm.
I still remember driving with the sales rep, and I'm like, this does not look good. And we're driving down like you could tell just terrible neighborhoods, and
Yeah, like
literally,
Yale. Were you at Yale?
Jeff, you're in the right area, and
I
I
meant the
literally.
actual school. Those Yale kids. You can't trust those Yale kids.
Actually, well, one time I saw the Super Collider at Yale, believe it or not, because they were doing
Oh
some
yeah.
work with
Oh.
PICs. I had they have an underground collider. I don't know if you know that
Oh,
or not.
cool.
It's
I didn't
like
know that. Yeah.
super cool. That was one of the most fun days.
Yeah.
That was a great visit. But so anyway, so driving down the road, and literally there is a car that is in the middle of the road that is on fire, and it's just abandoned. And there's like
Okay.
another like dead car. It was like one of these apocalyptic movies. It was really
Yeah.
really
Yeah.
crazy. And then he parks in front of this customer. I'm like, are we gonna like be alive? Fortunately, the guy was pretty big that I was with, so I felt he was could defend us. But
Yeah. Yeah.
we went into the customer, and I was surprised his car was still there when we left. So,
Yeah. Yeah. You made it.
and visited that customer many times, so it was pretty funny. But
Nice.
those were definitely some pretty crazy stuff. I'll share a last one, which is I was working with a customer who's doing a UPS design, and you were trying to debug it. There's some firmware issues with it, and so I just grabbed the guy's scope probe, and I see what looks like a ground that's on one of the FET heat sinks or whatever. So I go to grab
Uh,
it, and then attach the ground, and the guy, like the engineer I'm working with, like hit my hand, like knocked it away as quickly as he goes, stop. He goes, that's 400 volts DC with no
oh.
fuse.
Oh my.
And
And
yeah, that was my
but it was like
response.
a test point though that it was supposed to non-labeled, I
Exactly.
guess, huh?
Yeah, not labeled. And I was like, okay. I said, you will be placing all scope probes
That's right.
test points going forward. So
Yeah, I'm gonna get some
so
lunch. You just take care of this, and I'll be right back.
I will be right back. And that taught me a very important lesson, which is if you're not familiar with the design, then you might wanna be very cautious in where you
That's
place your
right.
scope probes.
That's right. Right.
Another learning, like very related to that, is containment chambers, and that is
Mm,
that if you ever do any kind of, you're talking earlier about high voltage, high current designs, and that is when things go bad, they go bad quickly, and things explode. And
yep.
a lot of customers are developing products like that. They'll have these like massive containment chambers, that are set to contain explosions. And if you are doing
Yep.
that type of work, I would highly advise you invest in something like that.
Yeah, yeah, and also the nice thing too is that a lot of there's like wireless DMMs now too, so you can like probe things, set it in there, everything's good to go. You can still see your reading remotely, and yeah, you're all safe. So that's nice.
Absolutely. Yeah, yeah. I've done that with OpenScope actually, because OpenScope can run
Oh
on its
yeah, yeah.
own USB power. So I'll
Uh
have
huh.
a
Uh huh.
USB brick that's powering up OpenScope, and you're exactly right. And I can do like high voltage power supplies and stuff like that safely with those, and not worry about blowing up my bench scope. So
Yeah. And OpenScope is Bluetooth based. Is that how that works?
OpenScope is Wi-Fi actually.
Oh,
So
okay. Okay.
yeah, so that particular implementation is all Wi-Fi. So
Cool.
it's pretty cool. And yeah, no, it's definitely it can be a savior in terms of not blowing up your test equipment, and then you
Yeah.
could say, well, I'll just use my laptop. But then the problem is you can get electrocuted by your laptop. If the laptop
Right.
ground is suddenly hot, from what
Yep.
you've connected to. So it's pretty important to keep track of high voltages, and then what is your ground reference, and making sure
Yeah.
that you're debugging safely. We've done some other things, like usually I'll do like USB isolators and stuff like that in
Uh
situations
huh.
like
Yep.
that. I'll take like a like a USB UART, like a MSP221A or something like that, and then I'll use like one of those optic isolators. No, not the optics. I usually use the capacitor ones from like
Yeah.
ADI or Silicon Labs, and then I'll
Yep. Yep.
put those in between, and then connect that to the system under test. That's a pretty standard solution for that, and then you can start doing debugging through it.
Yeah. Yeah, that's a nice thing to do. And those things, yeah, they do what, 5,000 volts, like RMS, something like that.
Exactly.
They're,
Yep.
they're real they're thick parts, but they do the job in the industrial
Yeah.
spaces for sure. Yeah.
Yeah, yeah. I'm glad I haven't worked on a design too much higher than that. There's a couple other ones. Like I had a customer that was doing a battery pack for buses for electric vehicles.
Oh yeah, yeah, yeah.
For electric vehicle bus, and the thing had what was it? It was like 32, battery. They're like they're battery management modules that
Hmm.
sit on clusters of batteries, and then each one of
Yeah,
those
yeah.
batteries is at a higher stack voltage. And I
That's
think the
right.
total stack voltage was 600 volts DC in this battery
Right.
pack. And and it had like an isolated CAN bus that would interface between all the MCUs that were doing all the battery management. And in that particular system, I was just like, I'm not touching anything here. I was
Right,
like,
right.
you need to put a scope on these points and collect this data, and I'm going to
That's
go in
right.
another room, and then you can then tell me what your
Yeah.
results are.
That's right.
So
Well, what's
it's
crazy about that is that you start to normalize to it. So I've worked on 1,200 volt systems that had like doublers, like all the way up to the 1,200 volt DC, and like you get used to it, and that's when it gets really scary. Is that you're like,
oh
oh
yeah,
well, I'll just move this over here and over here, and I've had it short in front of my face before, and it just
ooh.
yeah, that was okay. Well, I'm done for the day. I'm going home. See you later.
Yeah, yeah. My hat off to you, because I'm pretty
Yeah.
afraid of some of that high voltage stuff. I'm
Right.
afraid of actually becoming used to it. That's actually my
Yeah,
big
yeah,
fear.
exactly. That's
You
the
know,
that is the healthy fear because you get used to it and then you act in what would normally be innocuous kind of behavior at 5 volts DC, but yeah, you just got to be really vigilant the whole time.
Let me
So,
share another story you'll get a kick out of. So when I was a co-op student, when I was going to college, I worked for a
yeah.
electronics design company, and the manager there asked me to develop a plus and minus 1200-volt power supply, but at low
Okay.
current, like at just
Okay.
a few
Yeah.
milliamps. But it was to test a high voltage amplifier that we're building for another customer. And so I was like, I had an engineer that I was working under, great guy, taught me a ton, and he gave me kind of some ideas how to design the circuit. So then I designed the circuit, and then I did the layout. This was before we had CAD tools, so you did everything in Rubelith, and you know and and this tape that you would bend, and
Oh
you did
yeah,
all the
yeah.
layouts, manually back then. And the funny thing is, I still do layouts that way even today. I very rarely use automatic routing because I just enjoy the whole process of
Uh-huh.
of
Yeah.
routing traces. But anyway, so I designed this whole thing, and then the amplifier board, and then I needed a plus or minus 1200-volt power supply, and the engineer I was working on was like, well, just use a voltage doubler. I was like, oh, that's a brilliant idea. I can voltage double in either direction. I don't need that much current. And so I look in our stock, and we only have 100-volt electrolytic capacitors that are in stock. And I was like,
Oh.
hey, I said, these are only 100 volts. I said, we're going to, now remember, I was not an electrical engineer yet. I said, we're only going to 120 volts, not realizing that it's really 170, square root of two. And I said, I don't like using these, but it's all we have. He goes, oh, don't worry about it. You can use those. And I think he was trying to teach me a lesson. And
Yeah, yeah, yeah.
so,
Teachable moment here.
yep. So I went and installed 10 of the capacitors for the high side, 10 for the low. So you had a 10x doubler on either end, fired it up, and got plus and minus 1200 volts for about 30 seconds. And then
That's right.
all of a sudden I hear this, hissing,
Yep.
bang, and they
Yeah.
all went like popcorn. The
Yep.
capacitors, like literally the aluminum cans blew off of them. They were all over the lab. There was electrolytic fluid all over the place. It was
Oh man.
crazy,
It's
and
a risky lesson to teach if you're the engineer in charge there, but yeah, you came out with all your fingers and toes, so that's important, you know.
I lived through it. And
Yeah.
I'll tell you, I pay attention to voltage rating on electrolytic capacitors these days.
Yeah.
I don't think
Yeah,
I've ever
exactly.
made that mistake again. So
Well, that's great.
so it's definitely a good way. I think the best way, frankly, to learn is you just got to get out there and do it.
Yeah. Yeah.
I don't think there's anything else that's better than that. One thing, another comment, I'll give just some chops to Dave Jones. Like, he has his Tear Down Tuesday, and
Yeah.
and that's something that I love that idea. I've watched many of his teardowns, and in fact, I search for those. Like, if I want to learn about something, I'll usually go and look and
Yeah.
see if he's
Yeah.
got something. Because I just find it fascinating how much you can learn from tearing down an existing design, and then you really learn it when you try to implement it yourself. That's when you really learn that a lot of the very subtle design considerations, and
Yeah.
the stuff it takes you 2 to 10 times longer than you originally anticipated,
Yeah.
but that's, you're learning throughout the entire process.
Yeah, I can't name the number of times where I'm like, "Oh, I understand the system," and then like 3 months later, I'm like, "I had no idea how much more depth there was here." And it's sometimes just luck, sometimes I'm following a does app note or something like that. But you just like when you really, really dig in, you really understand the system. It's like that. It takes a while, and you need to look at a lot of different teardowns and similar things to get there.
Yeah, absolutely. And the teardown sometimes give you some good ideas, even of not just even electronics, but some mechanical. A lot of time when you're doing a
Yeah.
product, there's everything from the ID, industrial design aspects to it. There's how do you make it fit together? What's the molding look like? There's some weird things, UL requirements for safety, like spacing that's required, and
Hmm.
some of that kind of stuff. Like, how did they do it with these push buttons, and meet the UL safety requirements? So there's a lot you can learn from looking at teardowns, even if you just study like the dyes that were used for the injection molders for plastics. There's even like
Hmm.
subtle things there that the way a part is shaped, and the fact that it's angled because it's the only way they can get it out of the mold,
Oh yeah,
reliably,
right,
and
right.
things
Draft
like
angles,
that.
all that stuff.
Yeah,
Yep, yep.
draft angles, exactly. And it's stuff, and it's funny, like a normal consumer would never be thinking about that stuff. But
Hmm.
you tear it down as an engineer, and I love to just look at everything because there's all that kind of evidence is there in every product that you own. And it's just
Yeah,
there for you to look for it.
yeah. That's great. Well, John, I appreciate you tearing down your career here and letting us peek inside of what you've been doing. It's been really interesting to hear your journey at Microchip. It sounds like I mean you've done a lot of things there, and it's really interesting to hear all of your experiences there.
Oh, it's my pleasure. Yeah, no, I've really enjoyed the chat, and thank you again for inviting me to the Amp Hour, and and I seriously wish you the best of luck. Stay safe.
Great. Thanks so much. We'll talk to you soon.
Take care. Thank you. Bye bye.